So we're going to have a look at here is series resistance. The first one depicting the zigzag type of format that resistors are represented as, and the other one here just representing the resistor as a rectangle. You'll see either one or the other, in various textbooks. It doesn't matter, they all mean the same thing. These are series circuits, which basically means that this one is attached to this one and is attached to this one, and on a series connection. And we've done the same thing along here, for 4 resistors, and you can add as many as you like, to a series circuit. If you want to find out what the total resistance is of a series circuit, it's basically just equal to R1 plus R2 plus R3 and as many as you've got connected. You'll have a colour on your resistors, and they'll be printed onto the resistors, and each colour will represent a number, and as you can see there, we've got those designated beside each colour. Depicted on these are the colour bands. Here you've got orange, orange, red, and then over the far side here you've got gold. This one here is brown, green, red, gold. The gold band's right over the edge there. And this one here is red, red, brown, and then you've got gold over here. Now if you're reading these to work out the values, here you've got 3, 3, then you've got your multiplier, which is the red, so that will give you 3.3k, and then you've got the gold band here, which is telling us that should have a 5% tolerance range within 3.3k. This one here is 1, 5, and red again, so that's 1.5k. The gold band is a 5% tolerance rating, and this one here is red, which is 2, 2. Brown is 1, 0. So it's 220 ohms. And here we have some resistors with a colour designation of brown, black, red. So that's going to tell us that that's 1k ohms, and you can see a gold band at the end. So these are again a 5% tolerance, and the same for this one here. So these two are the same, so they're both 1k. So we're going to use the multimeter. This is a digital multimeter, and we're going to be measuring resistance. We need to turn it into this range here, which is for your ohms, designated down here. And as these are 1k resistors, we'll have to put it on to the 2k setting. So if we switch that over to 2k, you can see now the arrows pointing to where the 2k position is. So what I'm going to do now is just short out the leads, and what we'll end up with here is, I'll actually move it down to the 200, which will give us a better reading. You can see here that our lead resistance for the meter is 0.6 of an ohm, so we've got to take that into consideration. So what I've done is turn it back to 2k, because now we're going to measure the resistors. If we put our leads onto the resistors, you'll see that we'll get something other than 1k, and as you can see here, we're getting 1.006. So this resistor here, taking off lead resistance, is pretty close to 1k. We'll try the other one, because you can get variances in this. And this one here is reading 1003, so a little bit lower than the one before. You've got R1 and R2 connected in a series format, and their printed value is 1k ohms, and you normally see that as 1k 0, or you may see it as 1k ohms like that. With our resistors, we said they had a N band of gold, which is 5%. So knowing the value of the actual resistor, which is 1000 ohms or 1k ohms, you divide that by 100, and then you multiply that by 5, which represents the 5% tolerance range. You end up with 50 ohms. So now that's a plus and a minus. So your resistance tolerance value for a 1k ohm resistor is 1050 to 950. Our readings were 1005 we take off the lead resistance, which is the 0.6 ohms, and end up with 1400.4. We do the same for this one, which had a slightly lower reading, or closer to 1k. You take off the meter lead resistance and you end up with 1002.4. So all that's proving now is that the maximum range is 1050, the minimum range is 950, and what we ended up with was slightly over 1000 ohms, so they're both within the tolerance range for a gold band. We've connected onto a board the two 1k resistors, and theoretically what we should obtain now is a 2k ohm resistance reading. So we're just going to measure from this side of one resistor to this side of the other resistor, and that'll take the two resistors in series, and we should end up with something close to 2k. So we'll put one lead on there, the other lead on the other end, just let that settle down again, and you can see here we're getting almost exactly 2k. So if we switch down, I'm on the 20k ohm resistance range, if we switch down to the 2k ohm resistance range, we'll just get a more accurate reading. It's going overload, so it's actually slightly over 2k, which is what we would assume, and if we put on the 20k ohm, we're getting 2k. So it's just a little bit over 2k. It is the actual reading, but it's within tolerance for those resistors. So what we're going to do now is add another resistor to the series string. Now this time it's a much larger resistor. You can see here we've got brown, black, and then yellow, right? So what this is depicting is a 100 kilo ohm resistor, and it's got a gold band as well, so it's within that plus or minus 5% of that value. And what we're going to do now is add that to the board, and we'll measure the resistance now in series with the two 1k resistors. So we've added the 100k resistor in and put the value here. The actual measured value, which we'll show you in a minute, is 98k ohms. And over here in the black, we just worked out the right tolerances for that 100k ohm resistor. So again, you got the value 100k, which is the printed value on the resistor. Divide that by 100, you multiply that by the 5, which represents the 5% tolerance range, and that equals 5k ohms, which equals 5000 ohms plus or minus. So your tolerance range will be from 105k to 95k. We've got our 100k resistor. We're just going to do a resistance check on that, and we end up with 98.1. Before we got 98, but again, depending on how your contacts are, you will get various readings. We'll leave it at 98, but you can see that it is lower than the printed value. Just supporting our theory that as you add resistors in series, the value should increase. We'll just prove that because we can clip onto just one resistor on its own. You can see there on the meter, right, we've got a reading just slightly over 1k. Right, so if I move that to two resistors in series, and I'll just turn the scale up so it can measure it properly, you can see that the 1 plus the 1 makes 2, and now we're putting a large value resistor in, which will need to go up to the 200k because it's a much larger resistor. You can see here that we've gone up to now 100.1k. We've got 100k plus 1k plus 1k. Now you would expect to get 102k, but our reading is only 100k. Now the reason behind that is, remember, this one actually measured as a lower value on its own, whereas these two were just slightly over their printed value. So if we go back to the 100k on its own, you can see it's only reading 98.1, and if we go back with the two 1Ks in series with it, that's what's bringing it up to slightly, we're just on 100k ohm. So we're just going to add one more resistor, and And this one is blue, grey, red, so that's blue is 6, 8, and the red is the multiplier, so 6.8K, again gold banding, so it's a 5% tolerance. So we're just going to measure that 6.8K resistor. I've turned that down to 20K range, that's the lowest range that will read it on this meter. And if we put our leads on that, we should get 6.8 if it's good. We're getting 6.83, and if you work that out with reference to the 5% tolerance range plus or minus, you'd find that that would be within tolerance for that particular resistor. We've added in our 6.8K, we've still got our two 1Ks, and we've still got the 100K ohm resistor here. So we'll attach to the 100K ohm resistor, and then we'll measure at the first 1K. And you can see there that we're getting 99.2, remembering that this is slightly low, so it's adding that 1K in. Then we'll go to the second 1K. Now it's gone slightly higher again, this one being low, so it's almost up to the 100K value, or it is, so it's slightly over. And now we add in the 6.8K, and you can see there that we're getting 106.9, so we got a bit of variation in this one and these two, and the slightly lower one here. So just looking at the drawing on the board, here we've got our 100K, 1K, 1K and 6.8, and again we've got the measured values. And if you add up the printed values, these ones here, we should have got 108.8K ohms, so that's what we should have had. But because we've got slight variations in the readings, you can see here that the total resistance, which is R1 plus R2 plus R3 plus R4 in a series string. Then we've got our 98.1, our 1.005K, 1.003K, and our 6.82K, right? And we end up with 106.93, and we measured 106.9 on the meter. So we're just basically proving there that if you keep adding resistors on, right, the resistance value goes up. If we started subtracting resistors off the string, the resistance value would go down. When you're working with resistors like this, initially we shorted out the leads and we got this value here, which is that 0.6 ohms for our meter lead resistance. Now we didn't really take it into consideration here, and we didn't take it into consideration there. The reason being is that when you start getting to such high values, I mean 0.6 of an ohm is really nothing, you know, in these two areas. And realistically, in this area here, 1K ohm, 0.6 of an ohm wouldn't make that much difference. It would probably come into play if you were very close to the tolerance range for the resistor. But in saying that, I mean, if you're 0.6 ohms and you were slightly over tolerance, I think you'd basically say that that resistor was out of tolerance anyway. When you're dealing with low value resistance, like if you were measuring something in 10 ohms or even less, then that 0.6 ohms could be critical.